So this is Chapter 5, Section 3, and we're going to be discussing the applications of the fundamental theorem of calculus. So far, the main concepts that we've learned in calculus are integration and differentiation. With integration, we use to define the area, and with differentiation, we use to define the slope of a tangent line. So if we think about it, the slope is change in y over change in x, and the area is length times width, or we can view it as change in x times change in y. And the slope is essentially division, while area is multiplication. So these are inverse math operations, and this relates to the fundamental theorem of calculus in that the theorem connects these two concepts of integration and differentiation, and basically says that they are inverses of each other, or that they undo one another. So to briefly review, the first fundamental theorem of calculus says that if a function f is continuous on the closed interval ab, and capital F is the antiderivative of lowercase f on the same closed interval, then the definite integral of f of x dx from a to b is equal to capital F of b minus capital F of a. And remember that capital F of b or f of a means the antiderivative evaluated at b or evaluated at a. Now, if we look at this equation, we can rewrite it as capital F of b equals the definite integral of f of x dx from a to b plus the capital F of a. So this rearranged equation is helpful in many word problems or free response questions that you may see on the exam. And now let's look at the original equation before we rearranged it. For a more specific example, we can apply it to the acceleration function. So the integral of the acceleration function gives us the velocity function. If we evaluate the velocity function at the upper and lower limits and subtract them, this will give us the change in velocity. When we apply this to the velocity function, we get the final position minus the initial position, and this is the change in distance. Now let's look at an example problem. Starting from rest, a rocket accelerates for 7 seconds. If the acceleration function is 1.2 t squared, how fast is the rocket moving at the end of 7 seconds? If we graph this, the function will look something like this, and we're looking at the range from 0 to 7 seconds. So this is the area under the curve within the upper and lower limits. Now here's the first FTC again, and we know that the acceleration function is the same as the derivative of the velocity function, or in other words, the antiderivative of the acceleration function is the velocity function. Now let's take the integral of 1.2 t squared, and we get 1.2 t to the third divided by 3, and now we evaluate at the upper and lower limits, and this will give us 137.2 seconds. Now let's look at another problem. Let f be the function whose graph passes through the point 3, 6, and whose derivative is given by f prime of x equals 1 plus e to the x divided by x squared. Find f of 3.1. So from this we know that f of 3 equals 6, and what we need to find is f of 3.1. And this is where the rewritten formula for the first fundamental theorem of calculus comes in. So we have f of 3.1 equals the integral of f prime of x dx from 3 to 3.1 plus f of 3. We should note here that in this problem it gets a bit confusing because the given function is lowercase f prime of x, so the antiderivative of this given function is lowercase f and not uppercase f. Now we can solve by plugging in what we know. So to solve for the definite integral, we'll need to use a calculator.
If you're given a function 1 plus e to the x over x squared, and you need to find the integral of it within a set boundary, since you don't know how to integrate it, you have to use a calculator. So you go to Math, 9, and then you get the integral. So you have to first put in the boundaries, which are 3 and 3 plus 1, and then you put in the function, which is 1 plus e to the x over x squared, and then you have to put what variable you use, which was x, and then you press enter, and then you get your value. And an important thing to note is to not use only 3 decimal places, because if you use that value and then you divide it, only using, and if you only used 3 decimal places, then your end result and final answer might be wrong. So use like 6 or 7 decimal places for this value, and then round to 3 decimal places at the end.
Now let's look at another problem. Let f of t represent a bacteria population, which is 4 million at time t equals 0. After t hours, the population is growing at an instantaneous rate of 2 to the t million bacteria per hour. Find the population at t equals 3 hours. So let's write down what we know. We know that f of 0 equals 4 million, and f of 3 is what we're looking for. We'll apply the method we used for the previous problem, and so capital F of 3 is equal to the integral of 2 to the t dt from 0 to 3 plus 4. Because the rate is given in millions, we're going to substitute f of 0 in millions. So we just have to remember to add that back in our final answer. So to solve for the definite integral, we can use the calculator, or if we know the integration rule, we can apply that as well. And the integral is going to be 2 to the t divided by ln 2, and we'll evaluate at the upper and lower limits. And so this equals 10.099. We can add this to 4, and our final answer will be 14.099 million.